So in this video we are going to discuss uncertainty in measurements. So when you take measurements in our physics course, you're going to use all kinds of different devices, and some of those devices are going to be analog, like you see here, like a ruler, or like a dial or gauge on your speedometer of your car or your motorbike down here on the bottom, or digital, like a clock, like a wristwatch, or maybe a digital readout on something like your voltmeter. And the uncertainty of the measurements we take with these devices is going to be different depending on whether they are analog, or an analog instrument, or a digital instrument, and we're going to take these readings differently. For example, if we start with the ruler here, and let's say take a measurement that falls right where I'm drawing this arrow, about let's say that's 3.3 centimeters. It's important that I estimate this digit here after the decimal, because when we do analog measurements, we're going to add, when we do any measurement, we're going to add what we call a range of uncertainty in the measurement. So the range of uncertainty in this measurement is 1/2 of the smallest division of the instrument. So if we look at our ruler here, 1/2 of the smallest division, so I see that this ruler is divided up into 1 centimeter increments. So the smallest division is 1/2. So that means 1/2 of 1 centimeter, which is 0.5 centimeters, is going to be my range of uncertainty. So when we report this measurement of right here, I would say it's 3.3 plus or minus 0.5 centimeters. Just like that. And the reason we add plus or minus 5 centimeters is because there's no lines here in between the 3 and the 4, we can't really say whether it's exactly 3.3 centimeters, but we do know that it's less than 1/2 of a centimeter, so that's our range of uncertainty. Let's look at another example of this. So let's say that I'm driving in my car and my speedometer is pointed to this point right here. I might say that my car was going, let's say 34 kilometers per hour. Right? So I've estimated the 4's place here, and I see that this speedometer is divided up into 10 kilometer per hour increments. So I know that 1/2 of 10 kilometers per hour is 5 kilometers per hour. So I would say that the speed that I'm reading on the speedometer here is 34 plus or minus 5 kilometers per hour. All right. So for digital, it's a little bit different. For digital instruments, let's say this is a digital clock. So this, let's say, is our hours. So for digital instruments, it's a little bit different. We do not estimate any place on a digital instrument. So for example, if we have a digital clock like I have here, and let's say this is hours, and let's say this is minutes, I would say that the time is 1 hour and 15 minutes plus or minus. So the range of uncertainty is the smallest division of the instrument for a digital instrument. So the smallest division of measurement for this instrument is 1 minute. So I would say that it's 1 hour, 15 minutes plus or minus 1 minute. So it's 1 hour. 1 hour, 15 minutes plus or minus 1 minute. And the reason we don't estimate on a digital instrument like we did on the analog instrument, is we have no idea what the number is in this place here. It could be 0 seconds, or it could be all the way to 59 seconds. So we only know that it's greater than 0 seconds, or it's less than 59 seconds. So we estimate, or we say that the range of uncertainty for a digital instrument is plus or minus the smallest division of the instrument as a whole. Okay, so that's a little bit different. So keep in mind, whether you're using a digital instrument or an analog instrument, how to measure uncertainty properly. Okay. Now what we were just discussing is absolute uncertainty of the instrument you're using. So absolute uncertainty is the constant value associated with that particular instrument you're using. So if, for example, in our ruler example, the uncertainty of the ruler was plus or minus 0.5 centimeters, the uncertainty whether you measure 3 centimeters on this ruler or whether you measure 10 centimeters on this ruler will always be the same. It'll be absolutely the same, and that's absolute uncertainty. Relative uncertainty is found using absolute uncertainty, and that tells us how much of our measurement is uncertain. And there's two kinds of uncertainty. There's fractional uncertainty, relative uncertainty, and there's percentage uncertainty. So what is fractional uncertainty? So if I want to find fractional uncertainty, all I do is I take the absolute uncertainty and I divide it by the total amount of my measurement, and that'll give me fractional uncertainty. If I want to find percentage of uncertainty, I just take that fractional uncertainty that we found and I multiply it 100 to make it a percent. So why do I need two types of uncertainty? Well, for example, let's do two different measurements with the same ruler we had before. Let's measure 1 centimeter. So I'll measure 1 centimeter. And I'll measure 10 centimeters. Okay? So when I calculate the absolute uncertainty, for the 1 centimeter measurement, I find, so the smallest increment of this ruler is 1 centimeter, so half of 1 centimeter. I find that the absolute uncertainty of that measurement is plus or minus 0.5 centimeters. When I do the 10 centimeter measurement, the absolute uncertainty remains the same, plus or minus 0.5 centimeters. Well, what happens when we look at relative uncertainty? So, why is my pen not working? Relative uncertainty. Okay, so for the 1 centimeter measurement, we'll measure percent uncertainty in this case. So for the 1 centimeter measurement, so I take my amount of uncertainty I have and I divide it by the total measurement, and I find that, and then I multiply it, I multiply it by 100 to get my percent uncertainty, and I get, half over 1 times 100, I get 50%. So 50% of the total value I'm measuring is uncertainty. And notice that there's no units for this because it's a ratio. The centimeters and the centimeters are going to cancel out for me. Whereas if I was measuring 10 centimeters with this ruler, I would say 0.5 centimeters over a total measurement of 10 centimeters times 100 is only 5%. Okay? So when we use this ruler to measure 1 centimeter, it's way less accurate, or way less precise than when we use it to measure 10 centimeters, due to the fact that a larger percentage of the measurement is made up of uncertainty. So what happens when in your lab report or whatever you're doing, you end up with uncertain values that you've measured that you then need to do some math on? You have to add them together, you have to multiply them together. How do you combine the uncertainties in the numbers that you have just measured? Well, for addition and subtraction, it's quite simple. So if you have absolute uncertainties, or if your measurements have absolute uncertainties that you're adding or subtracting, you just simply add the absolute uncertainties. So if you look in your data book, it'll look like this. If your answer is y and you add number a plus number b, and the delta, these triangles here, represent uncertainty. The uncertainty found in A plus the uncertainty in B equals Y. The uncertainty in Y. So that's what the triangles mean in this case. They'll mean different things throughout the semester, so I'll tell you what they mean when they mean it. So an easier way to look at that is, for example, we have 10.1 centimeters that has an absolute uncertainty of 0.5 centimeters, and I added to 5.3 centimeters with an absolute uncertainty of 0.5 centimeters. This 0.5 centimeter uncertainty and this point, why doesn't this work? This 0.5 centimeter uncertainty plus this 0.5 centimeter uncertainty combined to be 1 centimeter of uncertainty, and the other values add together just like normal. Why isn't this pen working? Hang on. There we go. What if you have to multiply and divide? So multiplication and division is a little more complicated when you're combining uncertainties. So instead of combining the absolute uncertainties, you need to combine the percentage uncertainties. It's a very important thing. Don't try to add the absolute uncertainties, it won't work. So in your data books it looks like this. Your answer y, and you're dividing it by numbers a, b, and c. You find the percentage, or like this, or the fractional uncertainty like this. The uncertainty in A over the uncertainty in B, the uncertainty in B over the B, and then you combine all these and you get the fractional uncertainty of your answer y, which then you'll end up having to multiply by y in order to get your final uncertainty. So let's do an example, because I think it'll be easier to look at. Say I'm trying to find a pressure, and I have a force and an area, and that's how I find a pressure. So I measure a force of 20.1 plus or minus 0.5 newtons, and I'm applying it over some area that has a width of 10 plus or minus 0.5 meters and a length of 5 plus or minus 0.5 meters. So first things first, I do the math and I find that the pressure is 0.4 newtons per meter. Alright, so what's my uncertainty though? So to find this, what I need to do is I need to find the fractional uncertainty of each measurement. So, and then add those together. So if I take the force's fractional uncertainty is 0.5 over 20.1. The width's uncertainty is 0.5 over 10. The length's uncertainty is 0.5 over 5. I add these all together and I find the fractional uncertainty for my answer is 0.17. I then have to multiply this 0.17 here by p, like shown here, in order to get my absolute uncertainty of my measurement. So this 0.7. So I find that my final answer is 0.17 times 0.4, my answer from up above, and I get 0.4 plus or minus 0.007 newtons.